Here are 3 examples of calculating cell EMF from chapter 20. First of all, you have to remember that EMF is also known as about 6 different names. And I'll use those interchangeably a lot, and so do a number of questions. And so get the language down before you even try the math. Know that cell EMF, or EMF, is also known as the voltage, the cell EMF, the cell potential, the potential difference of the cell, the electromotive force of the cell. And remember that EMF itself stands for electromotive force. Any one of these means the potential energy difference between the cathode and the anode in an electrochemical cell. All these mean the same thing. Question number 1. So now that we know that there's 6 different ways to say the same thing, calculate the EMF of a cell based on this reaction right here. We've got aluminum plus iodine goes to aluminum plus 3 and 6 iodide minus 1s. Okay? To calculate the EMF of a cell, remember that we take E cell and we say that's equal to the E of the cathode, the standard reduction potential of the cathode. And remember the little circle right here means standard, minus the standard reduction potential of the anode. And so we need to break these guys up right here and decide what's the anode and what's the cathode. Okay? First of all, aluminum goes to aluminum plus 3. Notice how I picked out the half reaction right there. And then in the second reaction, we've got I2 going to I minus. I'll put the numbers in there now too. I've got 2Al going to some Al positive 3 right here. Okay, two of these there should be right here. And then 3I2 goes to 6I minus. The half reactions happen to be balanced for mass already. And I could go through the steps of balancing them for charge. And then since I was already given the balanced equation, I don't need to do that. But I need to decide which one's oxidized and which one's reduced, because that decides what the anode and the cathode are. Aluminum goes from 0 charge here to positive 3 here. This is called oxidation. And remember, oxidation is the anode. Iodine goes from 0 right here to negative 1. And so it goes down in charge. And so it's reduced. And remember, the thing that's reduced is the cathode, red cat, anox. Okay? The thing that's reduced, the cathode, goes first here in the equation. The thing that's oxidized goes right here as the anode of the E cell equation, or the EMF of the cell. Where do I find these standard reduction potentials? Well, the best place to look is on the yellow periodic table, because that's what you're going to have to use in the test. Now, not everything is given on here, and so occasionally you have to look in Appendix E in the back of the book, or there's some given in Chapter 22, and we'll do that in another sample exercise in a second. But the ones we're looking for here are aluminum and iodine. And if I zoom in on this just a little bit, we'll be able to see them here in just a second. Aluminum is right down here. And it goes from Al plus 3 to Al solid, just what we want, negative 1.66. So this guy right here, negative 1.66. Iodine, the iodine is right up here. And it goes from I2 to 2I minus. And it's 0.54, positive 0.54 volts. Positive 0.54 volts. Now, you'll also notice right away that there's a 2 in front of each of these. Does that mean that I need to double the voltage? You'll also notice that there's a 3 and a 6 in front of here. Does that mean that I need to multiply the voltage by 3 or 6? No, it doesn't. Don't change these. Do not change these no matter what, because remember, voltage, or standard reduction potential, is what's known as an intensive property of matter. It's independent of the amount of stuff you have. Now take these numbers that we got off the standard reduction potentials page and plop them in for anode and cathode. Our cathode is positive 0.54. Our anode is negative 1.66. Remember, I keep the minus sign in there because we're finding the potential difference. And when I subtract those two, I end up with approximately 2.2 volts or 2.20 volts. That's the first example. Let's look at a second example. Have some paper out. Pause now if you don't have this all copied down so then you can write these notes down as well. The second one now says a voltaic cell is based on these half reactions. Some nice little crazy reactions here for you to look at. We've got indium plus 1 going to indium plus 3 and 2 electrons. And then we've got bromine, Br2 right here, plus 2 electrons goes to 2 Br minus. It tells us that the EMF of the reaction, or the voltage of the cell, is 1.46 volts. Using data, probably from the yellow periodic table, calculate the standard reduction potential for indium plus 3 to indium plus 1. And you say, that's kind of crazy, because can't I just look this up on the periodic table, or can't I just look it up on some table? Maybe you could. It's not given on this list. Indium's not on here. And I don't think it's even in the back of the book. So you could Google it, but you don't get Google on the AP exam. And so they want you to solve for that. Remember that the equation for this is that the standard cell potential is equal to the cell potential for the reduction, or the cathode, minus the cell potentials, standard potential for the anode, okay? And if we know that the total for the cell is a difference of 1.46, then we can plop in the value for bromine right here that we can look up and solve for what indium is, okay? Now, if you look at this, you can see that bromine is written as the gain of electrons. Reduction is gain. Remember, rig. And reduction is the cathode, red cat. And so that value will have to go in here for the cathode. And for indium, notice how it's written as the loss of electrons right here. That will be our anode. That's the thing we're looking for. So let's look up bromine on the periodic table. Let's see, without zooming in too far, I can find bromine on here right up on the top. Can you guys see that? I'll zoom in on it a little bit. You can see that it's Br2 plus 2 electrons goes to 2 Br minus. Oh, we're not, yeah, that's what we're going to. Br2 plus 2 electrons goes to 2 Br minus, which is right here. And this is 1.07. Pretty high standard reduction potential, so that means it's probably almost always going to be a cathode because it's got a pretty high EMF. 1.07 minus E of the anode right here. That's the thing we're looking for. Zoom out on this a little bit, and then it's just a little bit of algebra and say I'm going to subtract 1.07 from both sides. And then remember, I've still got my minus sign right here. And when I subtract these two, let's see if I can do this in my head. This is approximately, I'm just going to approximate, it's about 0.4. And then remember, this negative sign's here, so I'm going to bring the negative over here. So the standard reduction potential for this reaction right here, up here on the top, is about negative 0.4. I think it's, negative 0.39 if I do that. So E reduction circle for this is equal to approximately negative 0.4 volts. Okay, one last problem, one last example problem. Let's take a look at this fancy equation. We used one like this a couple of video casts before when we broke up and found out what redox reactions were and then balanced them. We actually balanced a big scary reaction like this, just like it, put the H pluses in, made sure that we had the right number of iodines, put the number of waters in, something like that. But now it says find the cell potential. Find the cell potential for this. Okay, first we need to break it up into oxidation and into reduction. And to do that, I probably have to go through and assign oxidation numbers. Oxygen, -2. Chromium right here. This is a tricky one to figure out. See how it's -2 times 7 is -14. It's got to add up to -2, and there's 2 of these here. So it must be +6. Chromium goes from +6 to +3, so it's reduced. Iodine is -1, and it goes to iodine 0. So it goes from -1 to 0, so it goes up in charge, so it must be oxidized. So my oxidation half reaction is 6I minus goes to 3I2. My reduction half reaction is the Cr2O7 2 minus goes to 2Cr positive 3. And then, of course, I'm going to need the waters in there to help balance it, and I'll need the H pluses in here too. But I'm not going to worry about balancing the half reactions. What I really need to know is which one's oxidation and which one's reduction. Because remember, red cat, this is my cathode, and anox, this is my anode. And to find the E circle at standard conditions of the cell, I need to take the standard reduction potential of the cathode minus the standard reduction potential of the anode. Don't forget to put the little circles there because they are mean that it's at 25 degrees Celsius, 1 molar solution, 1 atmosphere. Now I need to look up these two guys either on the periodic table right here, or since I know for sure that some of these aren't in here, I'll show you where they are in the textbook. A really nice list of zillions of these, and even some kind of strange ones, are in Appendix E of your textbook. E for electricity, E for electrochem. This is a listing of standard reduction potentials at 25 degrees Celsius. And just to give you a good idea, it kind of goes alphabetical. Here's the Cr2O7 plus 14H plus 6 electrons goes to 2Cr plus 3 plus 7H2O. It has a standard reduction potential of 1.33 volts. I don't know if you can see that very good. I'll zoom in just a little bit so you can see it. See, here's that one right there, 1.33 volts. We can write that down, and I'll get the other one for us for the iodine as well without having to zoom in and out. So our cathode right here, 1.33 volts, minus the anode, which is the iodine one. That one is 0.54 volts, and find the difference between those two, and I end up with positive 0.79 volts for this cell. So the standard EMF, or the standard voltage of the cell, would be approximately 0.8 volts. Good luck on your EMF calculation.